force, let's say, between the top of my head and the tip of my toes. And that tide means I'm being either stretched apart or squeezed. That's all a tide is. Now, on the surface of, say, the Earth, the tide is extremely small. That's why we don't think about it usually. Negligible. For the difference between my head and my toes. So it's just like 10 to the minus 6 Gs. Very negligible. Now, the water does tides because it's actually much more big. It's much bigger, much more massive. So it actually kind of deforms because it is bigger. So that's the key. If you want to avoid tides, you want to roll yourself into a ball. And if you want to go into a black hole, roll yourself into a ball. Now, if you stand on the Earth, of course, it's by definition 1G. The sun is also very low tides on its surface. Even though it's gravity, if you stood on the sun, you would burn your feet a little bit, but you would still feel about 28 Gs. Okay, this would kill you, but it actually you'll burn up before that, so it's okay. Now, a neutron star, like I talked about earlier, actually has a huge tide. You are going to die. This huge, it's almost 1 billion Gs. And if you try to stand on the neutron star, it's even worse. It's almost 1 trillion Gs. Okay, we don't want to do that. Let's move on. So how do you die by a black hole? Well, it depends actually on how big the black hole is. It turns out that the bigger the black hole, the longer you can survive. So how does this work? Well, we're going to just compute the tide from the tip of my head to the tip of my toes and ask what are the number of Gs. And we'll ask, when does it become 20 Gs? As you get closer and closer. That's the death line. And we're also going to ask, how long does it take for me when I'm falling in to reach the singularity? How long do I have so I can, I don't know, study what's inside the black hole and learn all its secrets before I die? That's exciting, right? I won't be able to tell anybody, but oh well. So a 10 solar mass black hole, it turns out you'll die far outside the horizon. This stands for 200 horizons. Okay, well, these are really nasty guys then. It means you haven't even entered the event horizon, you're already toast. So death by black hole is quite easy. You'll reach the singularity very fast. If you pass through the horizon, you'll reach the singularity in less than a millisecond, less than 1,000th of a second. Now, let's take the black hole that's in the center of our galaxy. It turns out that you'll die only once you're inside the horizon. When you're about 0.04 or some fraction of the horizon distance. And it takes a little while, 3 seconds, it's not much time, to finally reach the singularity. Now, the most massive black hole, that enormous guy that I told you about in the beginning, is almost a little bit more than 1 billion, 18 billion solar masses. It turns out that you'll only reach death when you're deep inside the horizon. And it will take about 18 hours for you to reach the singularity, and about the same time to reach that death position. So if you really want to fall into a black hole, I recommend the following. Choose the biggest guys. Now, it turns out that here's the kind of little twist about Einstein's relativity you probably are familiar with. If you're outside the horizon, you're watching somebody fall in, you never see any of this happen. Well, except for this, you'll see people die here, but all these people who die and hit the singularity, you never see happens. Nobody ever appears to cross the horizon. And this is because how time has pointed inward for them, but for you it still points upward. And when you have something perpendicular to each other, they don't communicate to each other. And in reality, all these black holes have big disks around them. There's lots of radiation, X-rays. You're going to be burned up before you do any of this, so don't worry about it. How much time?
I think we.
Okay. You mean out of time?
No, 5 few close.
Okay. So another couple of things. One is that you can actually get energy out of a black hole. Now, it's a really simple idea, but kind of complicated, so I'll just give you the really basic part of it. These are magnetic filings. You've taken a bar magnet that has north and south, and you've shaken iron filings around it. The field line is the definition of that thing which follows those little iron filings. That is what a field line is. Now, here's what we do. And this is how we think about black holes and how to extract energy. We think about those field lines as being inside the gas and the plasma. Now, if we look at the disk around the black hole, it turns out the disk brings in those field lines from large distance. And as it keeps on pulling in more and more of those field lines, they get close to that ergosphere. The ergosphere is that place where actually it's like spinning around. It takes space and time and spins it around and around. That's where the rotating energy of the black hole is. Now, if you have something like that's trying to rotate around and around, and I kind of try to grab it, it's going to try to slow it down, right? Well, that's what field lines do. When field lines enter the ergosphere, they're kind of heavy. So the black hole can't quite push them around as much as it wants. There's some resistance by the field lines, and it slows down the black hole. And this is actually how the field lines extract energy out of the black hole, by resisting the dragging of the space and time that is happening because the black hole spins. And this is how jets are probably produced. All those jets that burned us alive with 10 times lethal dose, etc., these are probably produced by this black hole ergosphere. Here's another picture of a jet that's from one of these galaxies. So one last thing, some fun stuff, is what about wormholes and warp drives? How are these related to black holes? Well, it turns out they're kind of like black holes, but it's just that time flows in a slightly different way, depending upon which one you're looking at. But I'm just going to really quickly kill this because there are so many problems. It turns out that in either case, a wormhole where we connect to some other part of the universe, or even warp drive type solutions. Now you may say, just a second, it may sound crazy, what am I talking about, warp drive, isn't that Star Trek? Well, it turns out that about 10 or 15 years ago, people actually started developing so-called warp drive solutions to Einstein's equations. And this is one of them. And the idea is that you actually sort of pinch the space and time in front of you, and you kind of expand it behind you, and it pushes you forward. But this actually has a really big problem. Both of these, wormholes and warp drives, require something exotic called negative energy. We have no idea where this would come from. It could be purely mathematical, which would mean that it's just that the theory is making up garbage. Another thing is that the warp drive solution, it turns out that you already have to have a time machine to create a warp drive. Well, if I had a time machine, I would go in the future and buy a warp drive. I wouldn't try to create one. Another big issue is that both of these systems are unstable to so-called quantum noise. And what it means is that it's kind of like the following. Anytime you try to start your car explodes. Well, that can't be too good. So when you try to start up your wormhole or you try to start up your warp drive, you explode. Oh, well, okay, so it's not going to work. So we're not going to be flying around like Captain Kirk anytime soon. Now, let's go a little bit beyond Einstein. Now, here I show the different scales and meters of a person, a blood cell, an atom, a nucleus, and possibly even an electron, which has to be smaller than about 10 to the minus 23 meters. What is beyond Einstein? Beyond Einstein means that we're talking about merging quantum mechanics on one hand with his gravity on the other. And this is what we call supergravity or quantum gravity. It's a merging of all the forces, and it happens at very high energy. Well, where do we know something that's really has a lot of energy and a little amount of space? The black hole singularity. The black hole singularity is a place that tests some of this theories of, say, the theory of everything or quantum gravity. Well, that's great because, well, if I fell into a black hole, maybe I'd learn something. But like I said, you would never extract that secret. So, oh well, okay. But anyways, it turns out that once you reach a certain scale called the Planck scale, that space and time no longer behave like in Einstein's theory. It starts smooth, but as you get smaller and smaller, it begins to get rough. Finally, at the Planck scale, space, time, and even sense of cause and effect are all mixed up. And it looks like a bunch of loops. You can have little baby universes form, loops form, cusps form, all sorts of things form. This is what we think the singularity looks like. It's this sort of bubbly, foamy, quantum stuff. And it all happens at the so-called Planck scale. By the way you get the Planck scale is you just play around with all the constants that we know in nature and make a length. So you have Newton's gravitational constant, the speed of light, and so-called Planck's constant. And you can play with them and you get that scale. Okay, let's review. So gravity is the curving or warping of space and time. Attraction is nothing more than following straight lines in that curved space and time. The ergosphere stores black hole rotational energy. It's a place outside the event horizon. So it's a way, it's actually there for our taking. We can get rid of it, extract it, do stuff with it. And it's a way in which jets are produced, these things that are very dangerous to us but are very interesting at the same time. Nothing can escape the event horizon. This is actually how it's defined. And when you fall into a black hole, you reach singularity in a finite amount of time. Okay, so I'm almost done. These are the three overall main ideas I want you to take home tonight. The first main idea is that a giant black hole sits at the center of every galaxy, pretty much. And the size of the black hole is probably between 1 million and 1 billion solar masses, approximately. So these are really monsters out there, sitting in every galaxy. And remember, there are something like 10 to the 11, more than almost 1 trillion galaxies in the universe. So there are more than a trillion, about 1 trillion black holes out there, massive ones. The other neat thing is that black holes are black, but they feed on gas. And that gas heats up, and that's what shines. The key thing is that black holes are so compact that they can suck up so much gas, get it so close, and get it heated so hot so that it shines very brightly. So in a black hole system where there's a disk and there's some gas around it, it's right next to the black hole where all the light comes out. That's where it's really, really bright. You can almost neglect all the other stuff because it's so bright. When we see all those X-rays, for example, from X-ray binaries, they're all coming from very close to the black hole. The final thing is that black hole rotational energy is outside of the event horizon, as I just got through talking a little bit a while ago, inside the so-called ergosphere. And remember, ergos means work. It's the place that you can actually do work on the black hole. You can extract its energy. And it's outside the event horizon, so it means it's not prone to this problem of always having to fall in. You can actually extract it. And it's a way in which jets are launched into a beam, like in this picture here. Okay, any questions? And thank you.
We're going to have time for a few questions, and I'm going to ask John to repeat the question because people in the back may not be able to hear. So let's start here in the